Good evening.
Good evening.
Yes, I don't know, but it looks like today our numbers are really low. Because I think we are currently 3 minutes. I
Let me dial them in. Let me dial them in.
uh, so we've allowed 10 minutes, but still we are not coming.
Let me try to draw the attention of others and see if we can get some numbers to join
Okay.
us.
Okay. Okay. So I think we can begin now. So I would share my screen. Okay. So today we'll be closing multiplexes. So you solve questions on them, etc. Yesterday we were able to solve questions on adders and subtractors. So for the purpose of our exams prep, we've closed that. So today we'll try and close magnitude comparators and then multiplexers. And interesting enough, I think we did treat magnitude comparators. I think that was last week Sunday. Yeah, last week Sunday. But then the numbers we had was really low. So I would open. I'll put out an open question. Should we first summarize all concepts under magnitude comparators first before we start solving questions, or you think we should go straight to solving questions?
Yeah, I think we should summarize it before.
All right, so let's have a brief summarization. Then we solve the questions. I think that will be fine. All right, so um, let's look at this. Let's talk about some of the most important points under magnitude comparators. All right, so we are there. All right, so under magnitude comparators, we said that they are basically combinational circuits. Okay, So when you are talking about combinational circuits, everything under others, subtractors, comparators, decoders, encoders, magnitude comparators, multiplexers, ring multiplexers, we classify all those as combinational circuits, basically because their outputs depend only on the inputs. Okay, the output do not depend on whatever is saved in the memory elements. It basically does not use memory elements. So it only depends on its inputs to determine its output. So uh, yes, please. Is someone saying something? I
No,
think
no.
okay. Okay. I think there was a sound feed outside. All right, so let's continue. So that was what we said. And we said that magnitude comparators, they can take as much inputs as are needed or as much bits as are needed to be compared. But this is what you have to understand with their behavior. Please, I believe we can all see the Y sheets. Please, can
Yes,
you
I can
see
see
the
that.
Y sheets? Okay. I just wanted to be sure that we will see it. All right, so we said that with magnitude comparators, they can take even 4 inputs, 8 inputs, etc., because their basic function is to perform comparison operation, and they compare in the form, or their outputs are in the form A greater than B. Let's start with equality instead. Their outputs are in the form A is equal to B, then A is greater than B, and then A is less than B. And their output is what determines its function or their function. So the basic function of a magnitude comparator, that it is just used to determine whether A is equal to B. So A will represent a particular input, okay, and B will represent another input. So assuming you have 2 different inputs, A and B, a comparator will be used to determine whether A is the same as B, which is A is equal to B, A is greater than B, or A is lesser than B. And that's basically the job it does. Okay. This is just the basic idea of a comparator that you need to know. It is just used to perform a comparison operation to determine whether one number is bigger than the other, is smaller than the other, or is equal to the other. That is all. So sometimes you might be giving up to, let's say, 4 input or 8 input. This is how to handle it. If you are giving 4 inputs in the form, let's say, 0, 1, and then 1, 0, okay, we call this kind of comparators a 2-bit comparator. Why do we call it a 2-bit comparator? Because you can see that it's comparing 2 numbers, which is 0 and 1, and then 1 and 0. And each of these numbers are 2-bit numbers, 2-bit binary numbers. If you count the bits, you can see that each number you have 2 bits in there. Okay, so we call this a 2-bit magnitude comparator. But if the inputs are such that you are comparing 1 and then let's say 0, this is your first input. So we'll call this input A, and then we'll call this input B. So if you have something like 1 and 0, so we'll call this a 1-bit comparator. Please, can someone tell us why we call this a 1-bit comparator?
Because one is having 1 and the other is having 1. It's 1 bit.
Exactly. Because each of the inputs that you are comparing here is made up of just 1 bit. So we are comparing 2 1-bit inputs. Hence, we call it a 1-bit comparator. All right, so assuming you are having something like 0, 1, 1, and then you are comparing this to, let's say, 1, 0, 0. So this here becomes your input A, and then this here becomes your input B. So which kind of comparator will this be?
A 3-bit comparator.
A 3-bit comparator, perfectly. So this is how we name comparators. So this is how we determine the type of comparator we are working with. But interesting enough, regardless of the type of comparator you are dealing with, the block diagram is the same. So here, if you are dealing with the last example, that is a 3-bit comparator. Here, our A is going to be 0, 1, 1, and our B is going to be 1, 0, 0. Okay, so someone can also decide to draw it in this form. Let me give another way to illustrate this. Someone can decide to illustrate the 3-bit comparator that we just gave in this form. So we had our input as 0, 1, 1 for input A. So we had 0, 1, 1, and we classify this input as what? A. And then the second set, we had what? We had 1, 0, 0. And then we classify this input as B. Okay. So the output is going to remain the same, which is A greater than B, A lesser than B, and then A equal to B. So we are going to have a 3-bit comparator. Okay, so basically we can establish a general analogy that comparators will take two inputs. Okay, two inputs in a form A and B, because we are saying that regardless of how many individual inputs we have, we will classify them into A and B before we perform the comparison. Okay, so assuming we have, let's say, 0, 1, 0, 1, and then 0, 0, 1, 1, we still do our classification into A and then B before we do the comparison. So it basically takes two inputs in a form A and B, and then it's going to return 3 outputs, or return a comparison output in the form A greater than B, A less than B, and then A equal to B. Please, are we all okay with this? So that we move on from here.
Well said, sir.
Okay. So now let us look at the block, the truth table of a magnitude comparator. And to illustrate the truth table, I'm going to use a 2-bit magnitude comparator. Okay, so if we're able to understand it, how to reduce a truth table for a 2-bit magnitude comparator, I think the 1-bit comparator is literally going to be an easy fit for us. So let's look at the truth table of a 2-bit magnitude comparator. So before we look at the truth table for a 2-bit magnitude comparator, please can someone tell us what a 2-bit magnitude comparator is? And then we use the definition to draw the block diagram.
Can you say it has 2 inputs and 3 outputs?
All right, so you said 2-bit magnitude comparator, it has 2 inputs. But how would the 2 inputs look like?
A and B. Oh,
A and B. You said you are comparing. So A will be like 0, and let's say 0 and 1. B can be something like let's say 1 and 1. Okay. So you realize that even though we will classify them as A and B, A has 2 individual members, right? And then B also has 2 individual members, making them up. Okay, so in total, this is going to have, so we name the first A0, then we name second A1. So we classify both of these as A. Okay, so what we just done, we said the first is A0, then we just call the second A1. And then the first here, we will call it B0. And then the second here, let's just call this B1, okay? So we are going to call this B0, and then we are going to call it B1. So A0, A1, B0, B1, they represent the bits, okay? The respective bits of A and B. And then we know the output is going to be 3. So let me do that properly. We are going to have equality. A equal B, A lesser than B, and then A greater than B. Okay, so this is our 2-bit magnitude comparator. Please, are you all okay with what we've done so far? Or someone has a question? Anyone with a problem so far? All right, so if no one has a question, then we can proceed with this, okay? We can proceed with this. Now, there is a general rule with comparators, okay? As you move forward, the truth table becomes much more difficult and complex. So if you were here during a session where we treated comparators, I gave you a much simpler or shorter way to go around this, or a much easier way to do this, okay? And then the method that I indicated that we can easily use to deduce the truth table for comparators is that we basically know that comparators, only one output can be high per time. So for 2 sets of inputs, you cannot have A equals B being high and then at the same time A less than B being high. What we basically mean by this is that, for example, if you have input 1 and 0 and you are comparing these two things, you cannot tell me that 1 is greater than 0 and the same time 1 is equal to 0. It's not possible. Per time, only one output combination can be high. Okay, so then it's very, very easy to deduce the scenarios where that can occur. So if you take your first 2 inputs, which is A0 and A1, and then for B0 and B1, we can just look at all the set of scenarios where equality can take place. Okay, so now let's look at the case for A equals B. The set of all inputs of a 2-bit magnitude comparator where A equals B can be true. Please, I believe we are all together.
Yes, please.
Right, so,
We are together.
okay, so let's look at the set of all combinations where 2-bit numbers or 2-bit binary numbers will be equal. We know that 2-bit binary numbers can be 0 and 0, they can be 0 and 1, they can be 1 and 0, and then they can be 1 and 1. Okay, so with these 2-bit binary numbers that we have here, when would they be equal? They will be equal when you are comparing 0, 0 to 0, 0. These two will be equal. And they will also be equal when you are comparing 1, 1, 2, 1, 1. This also will be equal. And they will also be equal when you are comparing 0, 1 to 0, 1. This also will be equal. And they will also be equal when you are comparing 1, 0 to 1, 0. This also will be equal. So these are the set of all possible combinations where equality can be obtained or attained under a 2-bit magnitude comparator. So with this, we can easily make a deduction, or we can easily deduce something from here. Now, let's make the deduction. Okay, let's make a deduction. We can deduce that this is equal when 0, 0 equals 0, 0. So for 0, 0, we know our first 0, 0. This is our first 2-bit, which is our A. So everything here represents our A, and everything here represents our B. So here for A, 0, 0, what is going? How do you express that in terms of A?
A0, A1. Oh.
Okay, so A0 and A1 prime. So we have A 0 and then A1. Then we take the prime of both. All right, and then at the right, that is B. How do you express 0, 0 for B?
B0, B1.
B0, we have B0, B1, and then all prime. And then plus, then we go to the second. We have 1, 1, 1, 1. You know 1, 1 is going to be A0, A1. Then 1, 1 for B is going to be B0, B1. All right, so let's continue. Then we go to C. We know 0, 1 is going to be A0 prime, A1. Okay. And then we know that at the other side, we are going to have B0 prime, then B1 plus. Then we have 1 and 0. We know 1 and 0 is going to give us A0, A1 prime. Then we are going to have for the other side, you have B0, B1 prime. So we see that we're just doing this, we've been able to deduce our expression correctly without having to even go through the process of drawing our truth table. If we were to draw the truth table, we would have had a total of 4 distinct inputs, which would have been 4 inputs. So to determine the number of possible input combinations on your truth table, you use 4 raised to the power 2. 2 raised to the power 4, sorry, 2 raised to the power 4, which gives you 16. So you would have had 16 possible input combination. And then you would have had to make the comparison for them one by one, one by one, one by one, and then take the outputs where A is equal to B was 1, make those deductions. It will take you a lot of time before you arrive at this conclusion. But once you're able to understand things this way, you can always be able to deduce your expressions very, very, very easily, okay, for both equality, lesser and then greater than, okay, without going through much hassle or struggle. But then we realize that this expression is not properly minimized. We can minimize this further. So you can perform minimization for this expression, okay? So if you intend to perform minimization for this expression, so we can proceed to so to perform the minimization for this expression, we can proceed to group, or we can proceed to do our groupings. Group like terms. So let's take this and then let me see. Let's take this. We have A0, A1 here prime. Let me see here. We have A0, A1. Here we have B0. All right, so here and this, I think we have B0, B1 prime, right? So we can have this right here. So we can group it to one side. So we have let me see, this side you have B0, B prime. So we take this out. We are going to have a new operation. I'm coming.
It will be confusing.
Yeah. So I'm coming. So here is B0, B1, this prime. So we have B1, B1. Okay, so I think it works rather this way. So let's take this. So let's take this and then this, and then we take this and that instead. So we have A0, A1. Please, there is a very short method. Okay, I just want to go through the long method before illustrating the short method to minimizing this. Okay, so we have A0, A1 here, then we have B0, B1, all prime. And then with this, we have plus. Then we have A0, A is prime. Then we have A1. Then we have B0 prime. Then we have B1 plus. Then now let's take this. We have A0, A1. Then we have B0, B1, all plus. Then we have the last one. We have A0, A1. Then we have B0, B1. So the B1 here is prime easy. Okay. So if we have this, we can factor, we can see that we have A0 prime here, we have A0 prime here. So we can factor A0 prime here. We have B0 prime here, we have B0 prime here. So you can factor B0 prime out also. So when we factor this out, what are you going to have left? We are going to have A1 prime, right? And then we are going to have A1 prime left here, and then B1. Oh, let me take this out. Then B1 here, right? B1 also has a prime. Yeah. So we have A1 prime left, B1 prime plus. Then for the right side, we have what left? We have A1, B1, right? Please can you all see what we just did here? Please can we all see what we just did here?
Yes, sir.
All right, so we come to the right side and then we replicate the same thing. So what does this have in common? We can take A0 here. And then what again can we take? We have B0 also as a common factor. Then we are going to have, so we have A0, B0. We are going to have A1 left and then B1, right? Then plus the other side, we have A1 prime and then B1 prime. Okay. So now this is what we have currently. So with what we have here, the values in our brackets. I believe this thing here looks familiar, right? If you remember, I think yesterday, I even restated a concept that if you have something like A prime, B prime, plus, let's see, AB, please, what does this represent?
XOR.
Okay,
X
so
no.
someone said XOR. Okay, so this represents an XNOR, right?
X no, yeah, X no.
Yeah, we said so this is XNOR, and then this year, I mean, if you get AB, A here is prime plus AB, and then here the B is prime. What does this represent?
XO.
XOR.
Yeah.
So this here is an XOR. Please, I hope we are all okay. Please, if you are not getting it, just let us know when you take it again. Okay. I just want everyone to be able to follow along. So please, are you all okay up to this point? Please, are you all okay?
Can you please repeat the A prime, the B prime plus the AB? You saying that it is X nor gates.
Okay. Okay. So let's take that again. So I was trying to illustrate a concept, okay? And we can literally see the concept repeat here in the brackets and outside it, okay? So according to the concept, we stated previously that our XNOR gate has a behavior, okay? And this behavior literally comes from if you have your inputs A and B. I just want to prove that expression there. If you have your inputs A and B, and then you perform your XNOR operation, that is let's say A exclusive NOR B. Okay. You have, let's say, 1 0, you have 0 0 1 1. Okay, so you know that the OR operation literally returns a 1 if at least one of the input is 1. But when you have exclusive OR, it only returns a 1 strictly when one input is 1. So this becomes 0. This here becomes 0. This becomes 1. This becomes 1, right? But then when you are dealing with your exclusive NOR, we invert the result from your exclusive OR. So we are going to get 1 0 0 1. Okay. So we are going to take the point where your output was 1 and then look at their corresponding input. So here realize that we had 1 here. What is their corresponding input? A was 0, B was 0. So please, can we express A to be 0 and B to be 0 in terms of A and B?
A bar, B bar.
Okay. So we are going to have A bar, B bar. And then for the second combination where our output was 1, what is the corresponding A and B input combination?
AB.
Good. So we have A and B. okay, which is A and B. So the resulting expression for an A X no B expression, okay, is what is A bar B bar plus AB. Please, can you all see where this law or rule is coming from?
Yes.
Exactly. So we can all see where this law or rule is coming from. So it means that whenever we see this thing here occur anywhere, okay, it doesn't matter which problem you are dealing with. Immediately you have the case of A bar, B bar, plus those equal to AB. You should know this is the X norm of the inputs. We can just here, we can just come and just say straight away and replace everything here in the bracket here as A0 bar, B0 bar. Then everything in the bracket, we can just say this is A X norm B, which is just like this. Okay. Where this one will be our first input A0, this will be our second A0 or B0. Okay. Then we have plus, then we have our A0, B0 bracket. We can see the same problem occurring here, right? At the other side. You see A1, B1 plus A1, B1, then the A1, B1 here takes all bar. And we know that when it comes to addition, A plus B is the same as B plus A. Okay, when we are dealing with our Boolean laws. So we know that this A1, B1 plus A1, B1 all bar is the same as A1, B1 all bar plus A1, B1, which totally mimics the law for or the rule for our XNOR gate. It means that this right here can also be replaced with A XNOR B. Okay, again. So please, can you see how the minimization is being performed? But please, after this, there is no need to actually know all the minimization process. I'm just illustrating it for just informative purposes. So after this, I'm just going to show you a very simple rule that kills the hassle of performing all this minimization for the sake of examination, okay? So after having this, we know that now we have the value in the brackets being equal, right? So we already know the law. If we have this, we group what is outside. So we have A0, B0, all bar, right? So we will group this in one bracket. That is what is outside here and what is outside here. We group it in one bracket. So plus, the symbol is, there is a plus, right? Plus A0, B0 into one bracket and then another bracket. Now we can see that the values in the brackets are the same now, which is A0, X0, B0. So please, do we repeat it 2 times or repeat it just once?
Just once.
Just once. So we have A0, X0, B0. So from here, what can we see happening in this bracket also? Please, can someone tell us, what do we see happening in that bracket?
Please, which brackets?
The first bracket, this first bracket here. We can see that this can be minimized
X no,
further, right?
X no.
X no again. So we just take our A, we just take our A 0, and then our X no, and then our B 0, okay? And then we just take our B0 for that. And then, oh, no, it seems I've done, please, kindly pardon me, please. Here, right at this place, we were supposed to have A1, B1 here instead. Please forgive me. Okay, so here was supposed to be A1, B1 right here. So we are going to have A1 X no B1 right here. So this becomes the final Boolean expression for our equality, okay, for a magnitude comparator. And this is what you're actually going to use to implement the equality outputs for our magnitude comparators. I believe we are all okay so far. So at this point, let me now tell you something here. If you analyze the final output carefully, you realize one trend here, that the final output for A equals B is actually an X norm of all your input combination. Okay, so the final output for an input combination, please, this is a general rule, regardless of the number of, how do you call it, bits you are dealing with, this rule holds. So if you are dealing with a 1-bit comparator, it's going to be A, X, no, B. That's going to be your equality, your expression for equality. So it's always just going to be an X no of your inputs. Okay, so if your input is A and B, then A equals B is going to be A X no B, because we implement equality with an X norm. Okay, so equality in magnitude comparators is implemented using an X norm operation or an X norm operator. So it's just an X norm of its inputs. So let's just keep that concept in mind. Okay, so the concept is that equality for magnitude comparators is the X norm operation of its input. So in this case, we said our input is 0, A0, A1, and then B0, B1. So then we are going to have our X norm of A0, X norm, B0, and then we have another bracket, then A1, X norm, B1, and that's it. And look, this isn't even manufactured. It is directly derived from this concept that we put out here, okay? If you want to determine if two numbers are equal, let me ask you a question. You have 0, 1, and then you have 1. Let's say you have 0, 1, and then you have 0, 1. If you know straightforward that these two are equal, right? How do you know these two are equal? You first compare the first, you first compare this 0 here to this 0, right? If they are equal, you now compare this one to this one. So what you are saying is that you compare this, the first 0 to the first 0 here. You know, this is A0, and then this is A1, and then this is B0, this is B1. So what you are doing here is that you compare A0, that is the first bit of the first binary number, to the first bit of the second binary number. So you are comparing the first bit, which is A0, okay, to the first bit of the second binary number, which is B0, okay. So A0, you are comparing it to B0. And we said that which comparator, which operator do we use for our comparison? X no. So you compare A0 to B0 using your X no operator. Then when you are done, you take your second bit and compare it to the second bits for your second binary number. Okay, so you compare if 1 is the same as 1. So that is saying that you are comparing A1 to B1. So you compare A1 to B1. And which operator are you going to use to do the comparison?
X no.
Yeah, X no, exactly. So that's how come we are even able to deduce this at the first place. Okay, so once you have this concept in mind, then look, you have taken yourself out of the hassle of having to do any of these things that we've done here. You don't have to do any of these things. You just draw this and you know that equality is the X norm operation of your inputs, and then you are done. All right, so let's take questions. Any question at this point? Then we look at less than and then greater than, and then we are done. Okay, so for less than and greater than, we are going to speed up with it, and then we solve our questions, and then we go. So any questions so far? All right, so then you presume that everyone understands, right? So when it comes to less than and greater than, you are going to do most of that, okay? So I'll just put the questions before us, and then we do that together. And then with the understanding here, the questions, you are going to solve most of them, okay? I mean, all of them, you are going to solve them, and then we indicate the answer, okay? So let's look at greater than and less than. It follows same concept in deducing the expression. So if you understood what we did previously, then I would believe that you would be able to do this with ease. Okay. So with greater than, we just have to know, we have to ask ourselves that what are the possible, what are the sets, or what are all the cases, okay? Let's call it cases. So what are all the cases where A will be greater than B? What are the sets of all cases? If we have, we can have 0 and 0, we can have 0 and 1, we can have 1 and 0, and we can have 1 and 1. And here is A, here is B. So, no, please don't mind me. So, here is 0, 0, here, and then here is A, right? And then for B, you can also have 0, 0, 0, 1, 1, 0, and 1, 1. So first with greater than, what are all the cases where A will be greater than B? Yes, can someone help point out some of the cases?
When A is 1 and 0. You know, when A
Okay,
is, yes, 1 and 0.
all right, so when A is 1 and 0, so someone is saying that case 1, when A is 1 and 0 and B is what?
And B is and B is also 1 and 0. Oh.
0 and 1.
0 and 1, okay. So when A is 1 and 0, and then B is 0 and 1, we can say here that A will be greater than B, right? Because 1 and 0 is greater than 0 and 1. So now let's look at the second case. So what is going to be our second case?
Can I also say that for our next case, when A is 1 0 and then B is 0 0.
Okay, so when A is 1 0
and B is 0 0.
is 0 0. Okay, so now let's just okay, so let's just take case 3 and then make our final deduction. So this A will also be greater than B, and then someone will also say that maybe when A is 0 1 and then B is 0 0, all these are possible cases. where A is greater than B, okay? But now let's make a very simple deduction here, okay? So if we make a very simple deduction here, we can then say that A is greater than B. For this, A is greater than B when case 1. So when case 1, when your first A here, okay, when your A is 0, you can see that if you have two numbers, okay, let's just take what is here. For case 1, you can see that the first one here, I mean the first bit, which is A0, is greater than our first bit for B, right? Which is first bit for B0. Please, can we all see that?
Yes.
And look, it's universal. If you have any two binary numbers, if you look at the first bit, and then the first bit, the first, let's say you have here we said 1 0, we have 0. If you look at the first bit and this one here is bigger than this 0, is there a need to even compare the second bits?
No.
No, there is no need to compare the second bit, because once the first bit here is bigger than the first bit here, you know this number here is bigger than, and it even applies to decimal numbers. If you are comparing, let's say, 55 to 45, once you see that the first digit here, because look, we said here is in ones, right? Here is in tens. So this is your MSB, your most significant bit. So if your most significant bit is telling you that this one is bigger than the most significant bit for these numbers here, then there is no need to even move to the next one, because you know that automatically this number here, the first number here, will be greater than the second. So a universal rule is that if your first digit is greater than the first digit of your first binary number is greater than the first digit of your second binary number, then automatically A0 will be greater than A0. Okay. So we've established this, right? So if we come here, we can also see that we said this is the first rule. So if this happens, then universally we can be able to conclude or make the assumption that your A is greater than B, because the first digit or the most significant bit of A is greater than the most significant bit of B. Okay. Or we can also have another scenario. And in this scenario, we can say that this happens for this kind of cases. Please, you can see that if you compare case 2, it's the same as case 1. The most significant bit of your A is greater than the most significant bit of case of B. Okay. So if you come and look at the third case, you can see something unique, that the first bits are equal. Please, can you all see that? Please.
Yes, sir.
Exactly. So we can all see that our A0 is equal to our B0 right here, right? So if the two are equal, then we can proceed to compare the second bit. So we say that, or if A0 is equal to B0 and the second bit, which is the second bit, which is the A1, right, is greater than our B1. So, and A1 is greater than our B1. Please, are you seeing what you are doing? So we said the first bits are equal. So if the first bits are equal, then you compare the second. Then if you compare the second, and then the first bit is greater than your LSB, okay, your least significant bit for your first binary number is greater than the least significant bit for your second binary number, then automatically you can conclude here that this is greater than this. Please, do we get the logic? Or we should take it again?
I'm lost.
You are lost. Okay. Okay, so
That part again. That part again.
all right. So please, are you referring to this part?
Yeah.
Okay. So what we said here, or what we're basically trying to establish here, is that if we take the case of case 1 and case 2, we can automatically see that say if please we all speak tree, right? So say if first binary number now, okay, in A, now comparing it to the first binary number in B, you can see say first binary number in A no, is automatically bigger or is bigger than the first binary number in D. So we automatically conclude that A is bigger than B. And a practical illustration is if you are comparing the decimal numbers, let's say 52 to 42. When you say how we know is in tens, right? Into who compare 5 and 4, 5 is bigger than 4. Automatically, when you say 52, is bigger than 42. Okay. So in your scenario where you can always draw a conclusion without even looking at second number. But then you say your other scenarios so where the first scenario will not be true. Okay. In the sense that yeah, automatically say first bit no for the first number no, bigger than the first bit for the second number. So that one will occur something like you have instead of 52 and 42, you have 52 and let's say 50. Okay, so you have 52 here and then you have 50. So with this, say try say compare first number 5 to 5. What do you think will happen? They are equal, right?
They are equal, yes.
So you first 5 no A0. Yeah, first second 5 no as B0. So you say A0 no, that's the first 5 no. And you automatically greater than our B0. Into yenya bibi say you have to now move and then compare these two now. Okay. So if A0 is greater than B0, okay, and then we compare the second one. Now you compare second one, then you say, oh, okay, for second one, A1, which is 2, is greater than our B1. That's A1 is greater than I'm coming. We said here it's equality, right? So if our A0 is equal to our B0, and then our A1 is greater than our B1, then we can draw a conclusion that the first number here is bigger than the second number. So please, I don't know if you now see what we did.
Yes, sir.
Okay. Please, are we cool with this? I think I'm not hearing from the rest of.
Yes, everything is okay with my side here.
Okay. Okay. So we just use the basic or logic for establishing if one number is greater than the other number. Okay. And so yeah, we now going to say, yeah, first time you establish equality, you see A0 is equal to B0. Into A0 equals B0, you see equality. You be using we all gate for equality, right? X no gates for equality, right? So here no, we can be able to establish no. The first rule was that if A0 is greater than B0, right? So if A0 is greater than B0, if A0 is greater than B0, how do we establish it? We said in binary numbers, you really have zeros and ones. So if A0 is greater than B0, then which one will take 1 and which one will take 0? Please, are you getting the question?
Please come again.
Okay. So we were saying that, all possible scenarios, no, you're saying if A0 is greater than B0, then you can conclude that the first number is greater than the second. Or if A0 is equal to B0 and A1 is greater than B1. Okay, let me give one last example, okay? And I believe this example should settle the case for most people. So we have 1 0 0 1, okay? And we have 1 1 1 0. I believe it looks a little bit complicated. But look, once you see it, you just can't unsee it, okay? Once you're able to just see how it works, you can't unsee it. And the honest truth is that unless you will be able to chew all the expressions, as if in the examination room you have to have questions where the expressions are needed or stated, and you have to deduce them for content. This method is the only way that you can be able to deduce them within a space of, let's say, 15 seconds or let's say 20 seconds, given the mode of our examination. So you said that say one number way and then number way. All these two are cases where your A is greater than B, because we said that you are remember that what you are even doing at the first place is for deducing the expression for A greater than B. So all these two cases are cases where A is greater than B. Okay. So from these cases, apart from these cases, you cannot get any other case again. Every other case will fall under this case, because we check a case we are compare first bits now. Okay, you can see that the first bit here is greater than the first bit here. So if the first bit here is A and the second bit here is B, you can see that A is greater than B. Okay, so immediately we see this happening, yenim say, we know that this, your friend is saying, we know that this number here is greater than this number here. Okay, because the first bit here is bigger than the first bit here. So now we've been able to establish where A is greater than B is coming from. Okay, then we can say that apart from this, we can also have another combination. So we say when A is greater than B, or first bit here equal. So honey, you check if first bit now, we cannot draw a conclusion. So first bit here equal. Okay, so first bit here equal. And your second bit now, you to me who say 1 is greater than 0, which means that A is greater than B. Then we can also conclude that your first number is greater than your second number, which expresses A is equal to B, or equally A greater than B, I mean. So that is how we're able to deduce A greater than B, or A equals B, and A greater than B. Please, can you all see the deduction now?
Perfect.
All right, so exactly. So once we've gotten the deduction, we know that this one was our first bit, right? Which is A0, B0. So A0, B0. A0, B0. Yenim say has to our first bit. So we have A0, B0. But yenim say last one is our second bit. So we have A1, B1. So now we just have to now convert this into numbers. Okay. This is just in the form of a logic representation, where more or less like a propositional logic. Okay. So we have to now convert our proposition to actual Boolean logic or mathematical logic, okay, where we use ones and zeros. So when is A greater than B? We know that binary numbers can only be 1 and 0, and A is greater than B when A is 1 and then B is 0. Are we right? Please, are we right?
Yes. Yeah.
Exactly. So we know that A is greater than B is true when A is 1 and B is 0. apart from this, you cannot say A is greater than B is true when A is 0, B is, it's not possible. Okay, so if A is 1, then we write A, right? Which is A1. No, A0, I mean, A0. And if our B0 is true, we write what? We know B0, 0 can be expressed as B complement, right? So we write our B complement. So we know all is plus. So let's just put this into brackets. So we bring our all is plus. And then we now have equality. So we said equality is X norm. So we are going to have all the X norm operation of our A and B, okay? And then we all know and is direct multiplication, right? So we open a bracket. And then another A1 is greater than B1. So when do we get A1 is greater than B? When A is 1 and B is 0. So we just bring our A, and then we have our B1 to be 0. So that's the complement of B. So this is just how to reduce the expression of A is greater than B. Very good. And then we use the same logic to deduce A is lesser than B. So deducing A is lesser than B. Let's make the deduction for A is lesser than B, okay? For the sake of time, we still not solve the question. So by 9:35, we are moving straight away the question. So what just happened here? All right, so for A is lesser than B, we said that the cases is when you have something like, let's see, 0 and 1, and then something like 1 and 0. It's just the opposite of the first one. And then you can have something where this and this are equal. But in the second one, this is smaller, this is bigger. Okay. So here, if you are to make the deduction, we said the first of all, we compare our first bit, right? So if the first bit here is smaller than the first bit here, that is A is lesser than B. Okay, then you can conclude directly that the first one here is bigger than this. Or if we check and the first bits are equal, that's A equals B. And then we check the second bit, so, and we check the second bit, and then our A is lesser than our B. Then we can also conclude that this is greater, okay? So we know here is A0, B0. Here is A0, B0. Here is A1, B1. So we know that for A to be lesser than B, here has to be 0, here has to be 1. So we are going to have A complement, and then B is 1, so B plus. So equality, we are going to have X naught, so A X naught B. And then we have our AND, which is direct multiplication. So we are going to have, so for this to be less, here should be 0, here should be 1. So we are going to have A prime, and then B, then 1 in this manner. So please, you see how quick we're able to make a deduction for A is less than B. Once you just understand the logic, you can be able to make your deductions easily. Okay, it shouldn't take you more than 10 seconds to actually successfully make your deductions. Are we together? All right, so
Yes,
with this, we can say that we are done with magnitude comparators. All right, so you can say we are done with magnitude comparators. Let me show you something here before we go to our questions. All right, I believe our slides are here. So once you can work with 2 bit magnitude comparators and 1 bit magnitude comparators are relatively easier. All right, so this is why you can see what we did here. So this is why 2 bit magnitude comparators reducing is difficult. Look, you have to come and do all this. So you have 16 different combinations, input combinations. You have to be able to represent all your inputs. And we are dealing with MCQ. You have to be able to represent all your input combinations one by one, like 1, baku 16. Then have to make your analysis for lesser, for equality, for, greater. Then after that, you now have to deduce your expression. After also, you have to come and use K-map to do minimization. Or if you don't use K-map, then you have to come and use your Boolean laws. To do all your minimizations, etc., etc. All right. But then if you will just understand how lesser works, you can be able to directly make your deductions and the corresponding expressions, okay, easily. All right, just as we did here. So we realize that we were able to make the deductions easily without having to go through most of this hassle, etc., etc. Okay. So now let's look at the questions and that's. Okay, so I believe we are here. So let's look at our questions. So we'll be very fast. So I read a question. If you know the answer, you can state it and then we move. Okay. All right. So 1, all the comparisons made by comparators is done using, okay, so all the comparison made by comparators is done using A, 1 circuit, B, 2 circuits, C, 3 circuits, and D, 4 circuits.
Two circuits. No, 1 circuit.
Okay, so someone is going for 1 circuit. Is anyone with another?
1 circuit.
All right, so 1 circuit is correct because you're only comparing A to B. So you only need 1 circuit to compare our A to B. Okay, so 1 circuit is correct. So let's go to the next. So I think this is a typo probably. So which one of these is not the outcome of a magnitude comparator? So which of these is not an outcome of a magnitude comparator? We have A is greater than B, B is lesser than B, C, A minus B, C, A is lesser than B, and D, A equals B. B. So please, do you all agree it's B? All right, so we all agree it's B, right? Because you all know that a magnitude comparator, the set of all possible outputs are A is greater than B. A is lesser than A is greater than B, A is lesser than B, and A equals B. So that means that the odd one there is A minus B. So if 2 numbers are not equal, then the binary variable will be, please let's look at this question technically. So if 2 numbers are not equal, then the binary variable will be A 0, B 1, C A, and D B. If 2 numbers are not equal, then the binary variable will be So can someone try? I mean, help us with the answer. This is a technical question, so let's have to look at it carefully.
I'm going for 0. That's A.
0. Okay, so please can you tell us why you are going for 0? Please can you help the others understand why 0 is true? Okay, so can you help the others understand why 0 is the answer? All right, so let's state why 0 is the answer. So if you look at this question, the question said that if two numbers are not equal, okay, then the binary variable will be, if the numbers are equal, what will be the binary variable? It's 1. Because we said that if equality is established, if A equals B, we put 1 there. Okay. So if it compares and the two numbers are equal, then a magnitude comparator puts 1 there. If the two numbers are not equal, then it's going to put a 0. Let me show you something here. So let me show you something here. Okay, so equality, you can see that if the two numbers are equal, that's x and y are equal, then x is equal to y will be 1. So you can see here again, but if they are not equal, for example, 0 and 1 are not equal, what is the binary variable? Is 0. 1 and 0, they are not equal. The binary variable is 0. 1 and 1 are equal. The binary variable will be 1. Okay, so whenever the two numbers are equal, x equals y will be 1. When they are not equal, x equals y will be 0. So that's the answer for question 3. So question 4, how many inputs are required for a digital comparator?
B. That's 2.
2. So 2 is correct. Okay, let's go to question 5. In a comparator, if we get inputs as A is greater than B, then the output will be A1, B0, C A, and D B.
The output will be 1. A.
Exactly. So the output will be 1. Okay, because if A is greater than B is true, then we put 1 there to denote that A is greater than B is true. Okay. So question 6, which one is a basic comparator? So we've mentioned this: A, X or B, X no, C, and then D, NAND.
X no.
Yes. X no, exactly. Because we said in a comparator, you cannot build a comparator circuit without an X no bit. So comparators are used in A, memory, B, CPU, C, motherboard, and D, hard drive.
CPU.
Very good. CPU is correct because comparators are used to perform logic operations, which is comparison. And then we said that in the ALU, it performs arithmetic and logic operations. So comparators are used to perform logic operations, which involves comparison in the CPU. So question 8, a circuit that compares two numbers and determines their magnitude is called, I think with this, everyone should get it.
A comparator.
Okay.
Magnitude comparator.
Magnitude, yes, magnitude comparator.
Magnitude comparator. Okay. Because we said that determines their magnitude. Okay, so it does not only compare, but it compares to determine their magnitude. So the answer is a magnitude comparator. So a procedure that's, oh, this question is, I think doesn't fall within magnitude comparators. Let's skip. Okay. So, but then the answer is A, which is algorithm, because algorithm is a procedure that specifies a finite set of steps. So let's go to question 10. How many types of digital comparators do we have? Please, how many types of digital comparators do we have? A1, B2, C3, and D4. I think we've not discussed this. We have two types of digital comparators. Okay, we have something we also call the identity comparator. The identity comparator is nothing different. For that one, it only checks A equal if two numbers are equal. That's equality. Okay. So the reason why usually we only study magnitude comparators, but not identity comparator, is that an identity comparator is already checked. That condition is already provided in the magnitude comparator. If you are building a circuit where you not need maybe lesser than or greater than, and you are strictly looking for only equality, then identity is okay. That one you can, if you take off the greater than comparator and the less than comparator, then the remaining circuit, which is the equal to comparator, is called an identity comparator. So we basically have two types of comparators in this regard. So an identity comparator is defined as a digital comparator which has only one output terminal, two output terminal, three output terminal, no output terminal. The correct answer is A. It only has one out. Exactly. Only one output terminal, because it only prints out A equality, which is A equals B. So it will have only one output terminal. So question 12. A magnitude comparator is defined as a digital comparator which has only one input, only one output terminal, two output terminals, three output terminals, no output terminal.
Two output terminals.
Are we sure? We are talking about outputs.
Okay, no, three output terminals.
Exactly, so three output terminals. So the purpose of a digital comparator is A, to convert analog input into digital, B, to create different outputs, C, to add a set of different numbers, and D, to compare a set of variables or unknown numbers. Yes. The purpose of a digital comparator. Okay, when we are referring to digital comparator, we are talking about magnitude comparators now. So here is D, to compare a set of variables or unknown numbers. And question 14. TL74LS85 is a 1-bit digital comparator, B, 4-bit magnitude comparator, C, 8-bit magnitude comparator, and D, 8-bit word comparator. I'm sure you might not be familiar with this. Let me see if that was addressed in the slides. We have already manufactured comparators, okay, which have already been made. So that one, you buy them, you can just infuse them into whichever device that. So if, let's say, you are building a machine that needs two comparators, instead of building the circuit from scratch, you already have pre-made circuits that have been built, okay. that you can just buy and insert them. So the TTL74LS85 is one of them. And that one is a 4-bit magnitude comparator. Its operation is for that of a 4-bit magnitude comparator. But since it's not directly addressing the slides, let's just ignore that. Let's see if we have other questions on the magnitude comparators again. All right, so I think that's all of the questions we have here on the magnitude comparators. Yeah, so I think those are all the questions we have on the magnitude comparators. Okay, so thank you for joining tonight's session. So unfortunately, you couldn't do multiplexes, or should we still start multiplexes since we have about 12 minutes left? Is what do you think?
Let's make it tomorrow.
Tomorrow, okay, okay. All right, then we are going to meet tomorrow. So please, I think the link is already on the platform. So let's try and then go through the questions on our own again, okay, and then go through that of multiplexes and demultiplexes also. So if God willing, tomorrow we will try to work on multiplexes. And if you understand multiplexes, we wouldn't spend my time on demultiplexes because they are just the opposite of one another. So once you understand one, you just have to invert the entire logic and then you get the other. And then we can move very fast to decoders and then encoders, okay? And after decoders and encoders, I believe that we can move straight away to sequential circuits and start looking at our latches, our flip-flops. And once we are done with sequential circuits, fortunately enough, sequential circuit is not so much, though it's a little bit technical. But I believe by Wednesday, I presume by Tuesday, Wednesday, we should be able to complete sequential circuit. And then we are going to look at finite state automata. And then I presume that by Friday night, we should finish with that. So if that happens, then on Saturday, we'll try and meet very early during the day and then we'll just solve questions throughout. I mean, as much as we can solve, and then I would believe that at that point we would be, I mean, there shouldn't be anything that will prevent us from getting our A's. Okay, providing you've done assignments and everything, by God's grace, I believe everybody should be able to ace the course. Okay. So thank you very much for joining tonight's session. We would meet again tomorrow, or you continue from here tomorrow.
Thank you very much for your patience and your time. Actually, some of us, we are gaining a little grounds on this concept.
I believe that by Saturday, we should have been able to cover everything holistically. Okay.
Thank you.